How's it going? Hope y'all are doing alright today. Yeah, that'd be fine. Just make sure if you come back later and you finish watching the video. But I'll go ahead and count it. Alright. Hope everyone's doing okay today. Do you have any questions so far? Do you have any questions regarding what we've done in this portion of the class, or if you have questions about work you're doing in the other portion of the class, just let me know. Finding the inverse. Okay. Is that what y'all are working on right now? Oh, of a matrix. Ah. I gotcha. Inverse of a matrix. Okay. Well, we'll do inverse of a matrix first, and then Geneva, once you find a good example, we can work on that as well. Yeah. Now, I think it's one. Is that a 2x2 matrix or a 3x3 matrix that we're finding the inverse of? Please tell me it's not 4x4. 3x3, okay. As you might guess, the amount of work becomes exponentially worse the larger the matrix gets. Okay. I will use, this is page 311, problem 42. Yes. It probably became pretty clear to y'all when you first started working these. Let's see. 1, 1, 2, 4, -3, 5. And there's a 3, -2, 4. Good. Okay. So the goal here is to find the inverse of this matrix. The way that we set this up initially, and I won't draw it quite so large this time, is we take our original matrix and we augment it with the identity matrix. Okay. So we took our original matrix here and we've added on, we've augmented, which means we made a vertical line and then we put a second matrix. We've put the identity matrix here. Now the identity matrix is one where we just have ones on the diagonal and then zeros everywhere else. Now the process of finding the inverse is similar to the row reduced echelon form we were talking about before. So the idea is that if we take this left hand side and use our three different operations that we can use and reduce the left hand side to the row reduced echelon form, then whatever is left on the right hand side should be the inverse. Okay, so if we take this and turn it into something like this, whatever is over here is, if this is A, then this would be A inverse. Okay, I will we'll go over that one next, Geneva. Alright, so the goal here is we still want to take this left hand side and simplify it to this. So it's the same set of processes or steps that we looked at before. We want to get a 1 in the upper left, and then get 2 zeros below that. Get a 1 in the middle, and then get zeros above and below, and then get a 1 in the lower right, and then zeros above. So the question is, how do we make that happen? Well, we already have our 1 here, thankfully. So let's make these two terms into zeros. So if we can just take row 2 and subtract row 1, 1 minus 1 will give us a 0. And we could do it either way. We could do row 1 minus row 2 or row 2 minus row 1. The order is not terribly important in this case, as long as we're getting 0 as the result. Now row 3 has a 2 there, so we need to subtract row 1 twice. Because if we could do 2 minus 2, that would make that a 0. So we'll do row 3 minus 2 times row 1. That'll result in a new row 3. Sorry. It's going to take some paper here. Now, what makes this more involved is that whenever we interact with a row, we have to work with all 6 numbers. Okay? So for row 2, we say row 2 minus row 1, so 1 minus 1, 0. Negative 3 minus 4, negative 7. Negative 2 minus 3, negative 5. 0 minus 1, negative 1. 1 minus 0, 1. And then 0 minus 0, 0. We'll repeat that for row 3, except now row 3 minus 2 times row 1. So 2 minus 2 times 1, 2 minus 2, 0. 5 minus 2 times 4, 5 minus 8 is negative 3. 4 minus 2 times 3, 4 minus 6, negative 2. 0 minus 2 times 1, 0 minus 2, negative 2. 0 minus 2 times 0 is 0. And 1 minus 2 times 0 is 1. Okay, that's our first step. Is we have the first column the way we want it. Now we need to work on the second column. So let's see. So if we want to take these two. You know what? Let's make this row positive first. So let's take row 2 times negative 1 and replace row 2. It's going to take a little work, but I think it would be better if that was a positive 7, because then we could just subtract 3 twice and to get that down to a 1. Okay. So 1, 4, 3, 1, 0, 0, 0, 7, 5, 1, negative 1, 0. We multiplied everything on row 2 by a negative 1 to make basically change all the signs here. And we'll leave row 3 the same, although we could, because most of our terms here are negative as well, we could multiply by a negative 1 also. Okay. So if we take this negative 3 and add it to row 2 twice, basically if we add negative 6 to 7, that gets us our 1 right here where we need it to be. So we'll take row 2 plus 2 times row 3 and replace row 2. So 7, and then 2 times negative 3, 7 minus 6 would give us the 1 that we want. Okay, so again, we want to make sure we do that for every single term on row 2. So 0 plus 2 times 0 would still be 0. 7 plus 2 times negative 3, 7 plus a negative 6 is 1, like we want. 5 plus 2 times negative 2, 5 minus 4 is 1. 1 plus 2 times negative 2, 1 minus 4 is negative 3. Negative 1 plus 2 times 0 is negative 1. 0 plus 2 times 1 is 2. Okay. From there, we want to zero out this term here and this term up here. So both of those need to become zeros. So for row 1, let's subtract row 2 4 times. So we'll have 4 minus 4 times 1. 4 minus 4 would give us a 0. And then for row 3, let's add 3 of these. Because if we take negative 3 plus 3, that'll make it a 0. So we need to add row 2 3 times. Okay. So the only row that's not changing is row 2. So I'm just going to write that one down again. Okay. So row 1 minus 4 times row 2, replace row 1. So 1 minus 4 times 0, 1 minus 0 is 1. We don't actually want to change this first column at all, so we have to be careful here. 4 minus 4 times 1. 4 minus 4 does give us the 0, like we want. 3 minus 4 times 1. 3 minus 4 is negative 1. 1 minus 4 times negative 3. 1 plus 12 is 13. 0 minus 4 times negative 1. 0 plus 4, 4. 0 minus 4 times 2. 0 minus 8, negative 8. Okay, so that's row 1 taken care of. Row 3. Row 3, we want to add 3 times row 2. So 0 plus 3 times 0, 0. Negative 3 plus 3 times 1. Negative 3 plus 3 is 0. And negative 2 plus 3 times 1. Negative 2 plus 3 is 1. And that's actually convenient, because that was the next thing we were going to do. Let's get a 1 right there. Okay, continuing. R3 plus 3 times row 2. Negative 2 plus 3 times negative 3. So negative 2 minus 9 is negative 11. 0 plus 3 times negative 1. 0 minus 3, negative 3. 1 plus 3 times 2. 1 plus 6 gives us 7. Okay, now not only did we get the 0, 1, 0 here like we wanted to, we also got the 1 on the bottom. So the only steps we have left are to make these two terms 0. And that'll be our last set of matrices. Let's see, so row 1, we can just add row 3 to that. Row 1 plus row 3 would cancel that out to a 0. And then for row 2, we'll take row 2 minus row 3, because 1 minus 1 will cancel that out to a 0. So row 3 is unchanged. Okay, row 1 plus row 3 replace row 1. So 1 plus 0 is 1, 0 plus 0, 0, negative 1 plus 1, 0. 13 plus negative 11 is 2. 4 and negative 3 is 1. Negative 8 and 7, negative 1. Okay. And then row 2 minus row 3 becomes row 2. 0 minus 0, 0. 1 minus 0, 1. 1 minus 1, 0. Now we see that the left half is now the identity matrix, and whatever we get over here will be the inverse of the original matrix. So again, subtracting negative 3 minus negative 11, so negative 3 plus 11 is 8. Negative 1 minus negative 3, so negative 1 plus 3 is 2. And 2 minus 7, negative 5. Okay. So right here we see the inverse of the original matrix. That seems to be it, Brandon. That's what was requested. That's correct, Luke. We're once we get the left-hand side to be the identity matrix, then whatever is left on the right-hand side is the inverse. I don't know if she taught you any other way, but regardless, they're all kind of tedious. Tedious is a good word for it, you know. Now again, technology will do all this for you if we know how to use the technology. So whenever if you end up having to do any of this in a professional capacity, then yeah, we could certainly use technology for that instead. Here, what we're really demonstrating is our level of attention to detail, because if we can do this accurately, it really indicates a high level of attention to detail, and shows that you can do a complicated process from start to finish, and keep track of all the important pieces of information throughout the process. So being successful at this class, and having that on your transcript indicates a certain level of acumen as far as how comfortable you are, one, working with new ideas, and two, being able to to handle a multi-step process with new information and successfully arrive at the answer without getting anything wrong there. Yeah. Any more questions on the inverse here? Notice we started with this matrix. Not a whole lot of similarity to the resulting matrix, as you can see. So the inverse and the original matrix don't necessarily have to look alike. That doesn't necessarily mean anything, really. But if we were to multiply these together, we should end up with the identity matrix as a result. So that's one way we could check our work, is if we multiply these two matrices and end up with the identity. And it should be this one times this one, not the other way around. I guess the other way around should work too, though. Alright. Let's move on to Geneva's question, which was page 322, number 17. For whatever reason, this problem is circled in my book, which was given to me by a different teacher than yours, so apparently it's a popular question to ask. Let me turn that light off for a second. Okay. A Colorado-based company makes artisanal dining room furniture. A buffet requires 15 hours for cutting, 20 hours for assembly, and 5 hours for finishing. A chair requires 5 hours for cutting, 8 hours for assembly, and 5 hours for finishing. And a table requires 10 hours for cutting, 6 hours for assembly, and 6 hours for finishing. The cutting department has 4,900 hours of labor available each week. The assembly department has 6,600 hours available, and the finishing department has 3,900 hours available. How many pieces of each type of furniture should be produced each week if the factory is to run at full capacity? Now, so let's start from the end. This is a matrix problem, but it's just a simple augmented matrix, not like an inverse. The goal is to find how many pieces of each type of furniture needs to be produced each week. So that means we have to figure out how many buffet tables, how many chairs, and how many tables are going to be created. So we use X for a buffet, Y for a chair, and Z for a table. Okay. Let me turn that light back on. I think it just looks better with the light on. Let me see it better with the extra light, because I already have my lamp and then another light over it. Alright. So X would be buffet tables. Y would be chairs. Let's see. Actually, we don't necessarily need variables here, but anyway. Okay. In fact, we could think of this like instead of well, it will be a matrix, but we can visualize it as a table, first of all. For instance, let's see. What three things do we have here? We have cutting, assembly, and finishing. I should probably do it the other direction. Let me start over. I'm sorry. I'm trying to lead up to something and I'm doing it opposite direction I need to be going. So cutting, assembly, and finishing. And we have a buffet. Chair, table, and we know we have total hours available for each one. So for a buffet, it was 15 hours for cutting, 20 assembly, and 5 finishing. For the chair, let's see, a chair requires 5 cutting, 8 assembly, and 5 finishing. And a table requires 10 cutting, 6 assembly, and 6 finishing. The cutting department has 4,900 hours available each week. The assembly department has 6,600 hours. And the finishing department has 3,900 hours. Okay. So setting it up like this, I think we can visualize it a little bit better now that I have it oriented correctly. So this is the hours that was required for cutting each of these types of furniture, and the total hours that we have available for cutting. Same for assembly, same for finishing. Okay, now looking at it like this is actually our matrix right here. 15, 20, 5, 5, 8, 5, 10, 6, 6, 4,900, 6,600, 3,900. Okay. So that's the direct translation of that into a matrix, because the idea is that, we have 15x plus 5y plus 10z equals 4,900. 20x plus 8y plus 6z equals 6,600. And 5x plus 5y plus 6z equals 3,900. Basically, we have three different equations, one for cutting, one for assembly, and one for finishing, and we have a total amount of hours possible for each. So the variable is the number of each type of furniture that we're making. Does that make sense how we set up the matrix here initially? Okay. Now, certainly from here, the issue is one of solving it. And essentially, what can we do to solve this? One thing is our goal is to basically reduce this to an identity matrix, so it's 1, 0, 0, 0, 1, 0, 0, 0, 1. And then whatever's over here is the number of each type of furniture that we should make afterwards. So, first thing I notice looking at this is all four of these numbers on the first row are multiples of 5. So I would say let's take R1 and just divide everything by 5 and rewrite that as R1. So 15 divided by 5 is 3, 5 divided by 5 is 1, 10 divided by 5 is 2, and 4,900 divided by 5 is 980. I should really get a calculator for that, just to be certain. Okay. It's a good chance for this last column we're going to be needing a lot of calculator work. Alright, so we have 20. You know what? We could reduce the second row by 2, although I don't know how much that would accomplish, actually. By 2 doesn't really change it by a whole lot. Now, the question is, how are we going to make this a 1? Well, I can tell you right now, it's going to be a lot easier with this being a 3 than when it was a 15. As far as how we can combine these together, the problem was because they're all multiples of 5, we weren't really going to be able to do a good job of canceling, making it into a 1. You could easily cancel out things here because everything's a multiple of 5, but making something into a 1 was a bit more tricky. Now that this is a 3, we have some different options. Now this is a little bit more elaborate, but what I would suggest is we can do 2 times row 1 minus row 3 and replace row 1. This 2 times 3 is 6. 6 minus 5 would give us the 1 that we need to get in this upper left-hand corner. So we do have to be a little bit more creative in this particular example. So we're not changing row 2 or row 3. So we do 2 times 3 is 6, minus 5 gives us 1. 2 times 1 is 2. 2 minus 5, negative 3. 2 times 2 is 4, minus 6 is negative 2. And 2 times 980, minus 3,900. So we'll go to the calculator for that. 2 times 980, minus 3,900. So that gives us negative 1,940. Okay. And so that gets us this 1 right where we need it, and we can use that to zero out the 2 terms beneath that. Remember that we work with this 1 column at a time. So we get this 1 where we need it, and then zero out the 2 terms below it. Let me get my book out of the way here. There we go. I'll leave that as a bookmark. Alright, so I'm going to come up here, and I'll just go ahead and rewrite that matrix just so we have it up here. Now, we see that we have a negative number here, but that's okay for right now. Until we get to the end, we won't know for sure. But when we get to the end, we should have positive numbers for all 3 of these, because ideally we'll be making positive numbers of furniture pieces. So if we don't get positive numbers, if we get negative numbers, we know that there's a mistake somewhere. And the last thing we want to do is try to go through a series of matrix operations and try to find one mistake. If it sounds like a needle in a haystack, that's basically what it is. Anyway, that's why it's important not to make any mistakes here. No pressure. Alright, so we need to zero out the 20. So let's take row 2 minus 20 times row 1. That'll give us 20 minus 20. And for row 3, we have a 5 there, so let's subtract 5 times row 1. So that 5 minus 5 would give us a 0. Okay, so 20 minus 20 times 1, 20 minus 20 is 0. 8 minus 20 times negative 3, 8 plus 60, 68. 6 minus 20 times negative 2, 6 plus 40, 46. And then 6,600 minus 20 times 1,940. So 6,600 plus 20 times 1940. 45,400. Probably we're thinking at this point, these numbers are a little too big. I don't know that there's a whole lot we can do to help that, though. This row is divisible by 2, but we can't go any further than that. So, that's why we have the calculators, to deal with things such as that. Alright. Row 3 minus 5 times row 1 replaced row 3. So 5 minus 5 times 1. 5 minus 5 is 0. 5 minus 5 times negative 3. 5 plus 15, 20. 6 minus 5 times negative 2. 6 plus 10, 16. And then 3,900 minus 5 times 1,940. 3,900 plus 5 times 1,940. And that gives us 13,600. What I would like to do at this point is simplify these terms a little bit. Row 2 we can divide by 2 at least. And row 3 we can divide everything by 4. The reason we don't want to divide by more than 2 is if we divide 46 by 2, we get 23, which is a prime number. And we can't go any further down than that, unless 46 is a factor of 68, which is not. Yeah, so we're kind of stuck there. So dividing this row by 2, that's 34 and 23. Oh, I'm kind of off screen, sorry. And then 45,400 divided by 2. I'm just going to do that real quick. It's 22.7. And then dividing by 4, we get 5. 4. And 13,600 divided by 4 is 3,400. Okay. Next, we need to get one of these two to be a 1. Probably, now that we've reduced these numbers a bit, it's a little bit easier to work with. Can we think of a number that we can multiply by 5 so that it's 1 away from 34? So we need a number that we can multiply by 5 that when we multiply those together, the result is 1 different than 34. Anyone know what that number is? Seven? Good. So if we can multiply this by 7, we'll get a 35. And then if we can subtract the 34, that'll give us a 1. So let's see, we'll take 7 row 3 minus row 2 and create our new row 2 based on that. Okay, 7 times 0 minus 0, 0. 7 times 5 is 35, minus 34 is 1. 7 times 4 is 28, 28 minus 23 is 5. And then 7 times 3,400 minus 22,700 gives us 1,100. Okay. So that gets us here. Now we want to zero out this 5. Alright. So, as we keep going, these numbers should get relatively smaller. and closer to, like, well, it should turn out to be fairly low positive numbers, I would expect. Not low, but like maybe in the double digits, not like hundreds. That's what I mean. Yeah, some of them may be single digits, I'm not sure. I guess we'll find out. But we want to make this a 0. Now we have a 1 here already, which is great, because now we can just take row 3 and subtract row 2 5 times, because 5 minus 5 would give us a 0. Okay. Okay. New page. So row 3 minus 5 row 2 replace row 3. That means we're not changing either of the first 2 rows. Okay. So row 3 minus 5 row 2. So 0 minus 5 times 0, 0 minus 0. It's kind of a formality, but we want to make sure that's still 0. 5 minus 5 times 1. 5 minus 5 is 0. 4 minus 5 times 5. 4 minus 25 is negative 21. And 3400 minus 5 times 1100. 3400 minus 5 times 1100 gives us negative 2100. Okay. So that takes care of our last operation there. And now we keep going. Now, next thing we need to do is make that negative 21 into a 1. And by the time we get to this step of the process, hang on, I feel like I forgot something. Not that one. That one. In fact, I should have done that at the same time as the last one. Sorry about that. Anyway, we'll do this one next. But we do need to take this negative 3 and make it a 0 first. So we'll take row 1. We have a negative 3, so if we can add this 1 3 times, negative 3 plus 3 would give us the 0. So we'll take row 1 plus 3 times row 2 and replace row 1 with that result. So row 1 plus 3 times row 2. So 1 plus 3 times 0, 1. Negative 3 plus 3 times 1, negative 3 plus 3 is 0. Negative 2 plus 3 times 5, negative 2 plus 15, 13. And negative 1,940 plus 3 times 1,100. Negative 1,940 plus 3 times 1,100 gives us 1,360. Okay. Now, we want to make this into a 1. Once we get to this stage of the matrix where we already have 2 zeros right here, we want to make this a 1. The only operation we can do is divide by whatever that number is. This bottom right 1, we always have to achieve by this division. So we want R3 divided by negative 21, replace R3. If we use either of the other two rows, then we'll change our zeros here somehow. And we do not want to change our zeros that we worked so hard to achieve. That's kind of ironic when I say it that way. Anyway. So we're just dividing row 3 by negative 21. Now this is great. Let me make sure I write that correctly. Okay. This is great because both of these numbers are evenly divisible by a negative 21. So we get 0, 0, 1, and then 100. Once we divide that by negative 21, we just get an even 100. So right now that means we're going to be making 100 tables. That's what it sounds like. Okay, but we still have to figure out how many chairs and how many buffets we can make. So we need to zero out these two numbers. Okay. And so to make this 13 a 0, we'll have to subtract row 3 13 times. 13 minus 13 would make a 0. So row 1 minus 13 times row 3. Replace row 1. And for row 2, we have 5 right now. We want to subtract 5, so 5 times row 3. Okay, this should be our last set of operations. Alright, so for row 1, we have 1 minus 13 times 0, is just 1. 0 minus 13 times 0, still 0. 13 minus 13 times 1, 13 minus 13 is 0. And then 1360 minus 13 times 100. 1360 minus 1300 leaves 60. Okay. And then for the middle row, 0 minus 5 times 0, 0. 1 minus 5 times 0, 1. 5 minus 5 times 1, 5 minus 5 is 0. And then 1100 minus 5 times 100, 1100 minus 500 leaves 600. So 60 buffet tables, 600 chairs, and 100 tables. That's what will optimize the production of this facility. Which is nice, because then they're making 6 chairs to a table, which is right about where it should be. Luckily, that turned out to make sense. Does that work? Any questions there? I didn't say it was easy, unfortunately. But yeah, we go back to where we started. And then by the time we're done, then we get the number of buffet tables, the number of chairs, and the number of regular tables. Yeah, pretty involved. How's the wonder how y'all are going to test on this. I guess it'll be online testing. I mean, it's almost noon and we've worked 2 problems. And I knew exactly what I was doing along the way, except for that 1 or 2 odd mistakes I made. No exams in this class. I do eventually plan to give you homework, but goodness knows when that's going to be. I don't want y'all to worry about it. But no, we don't have any exams for this class. Basically, part of this class grade is the exams you take for the other class, which is the mastery quizzes, I think is what she called them. Okay. Did you all have other questions? How are you all doing in general with the matrix operations? Are the individual operations that we're doing, does that make sense? Is it really just that it's so much stuff that it makes it a daunting experience? In order to save time on tests, sometimes what we do is we'll give you a 2x2 matrix, for instance, to find the inverse of. Or for a problem like this, we'll have you set up the matrix that needs to be solved, but maybe not actually solve it. Okay, so we can demonstrate the skills in maybe the 2x2 setting, just to show that we have those skills, while at the same time we demonstrate an understanding of how to create a matrix in 3 variables, like we do here, where the first part of the problem was creating that matrix, and then maybe we don't ask you to solve it in this case because there is so much to it. And actually, the early steps of this one was kind of tricky, just trying to get that 1 in the upper left hand corner. The easiest thing that we could do is we could have just switched row 1 and row 3 and divided row 3 by 1, or sorry, divided this row by 5 just to get a 1 there. But dividing by 5 would have given us a decimal right here, so I was trying to avoid doing that. So, to avoid doing that, I took out the common factor here of 5, and then I utilized the 3 and the 5 to come up with a 1. Basically 2 times 3 minus 5 is 1. So we can be creative. That's not an obvious process by any means. But like I said, what we tend to have you do is demonstrate your knowledge of working with matrices using simpler examples, like with 2-dimensional matrices, or 2x2s, sorry. And then like finding the inverse, or row reducing an augmented 2x2, rather than a 3x3 with augmented equal sign. Hopefully, that is what you do, although you may have to demonstrate at least one 3x3. It just depends on what each professor believes that you need to do to meet the course requirements. So, anyway, let's do something a little simpler than that. For whatever reason, they have us covering section 1.1 this week. 1.1 is pretty easy. It's really about the order of operations. That's ultimately what's happening here. And it talks about some of the properties of working with real numbers, such as a commutative property and associative property. Probably those are not as important to know as long as we're comfortable doing those things, which we are. We just don't know what they're called. But the commutative property basically says that 3 plus 2 is the same thing as 2 plus 3. Okay? Which I think we knew that without being told. So the idea with the commutative property is that the order can be reversed. So we can just easily add 3 and 2 as we could at 2 and 3, and that the order does not affect the outcome. Now, this is not true of subtraction, so it's a commutative property of addition, specifically. Because if we did 3 minus 2 and then 2 minus 3, those would not be the same thing. Similarly, we have an associative property of addition. And I believe they work for multiplication as well, but not division or subtraction. And the idea with the associative property is that we associate these two things in parentheses, so 1 plus parentheses 2 plus 3. If we change where that association is, instead of 2 and 3, we put 1 and 2 in parentheses and leave the 3 separate. The idea is that we still have the same sum once we finish. Whether we add 2 plus 3 first and then add 1, or whether we add 1 and 2 first and then add 3, either way we're going to get 6. Okay, that's the associative property of addition. Now these also apply to multiplication. But more importantly, they do not apply subtraction or division. Okay. Most of you are already familiar with the distributive property of multiplication over addition. Um, in this case, it works for addition and subtraction, but inside the parentheses. So we could have 2 times 4 minus 3 is 2 times 4 minus 2 times 3. That's just distributing the 2 to each of those numbers. 2 times 4 minus 2 times 3. And the same is true as if the numbers are added. Okay. So I would comment that that also includes subtraction here when we look at this distributive property. Now, all three of those things, commutative, associative, and distributive properties, probably you're familiar with just by working with math in general, although you may not have had a terminology associated with it in your mind, and you may still not, which is okay. The main thing is that you know how it works, and that's the goal. Okay. I mean, it's nice to know the word for it, but at this level, it's not strictly necessary. This is actually items that we study in higher level mathematics, but we look at things on a very general scale as we try to prove why different things are true based on that. That's neither here nor there. But let's look at our order of operations. And most of you are familiar with this already. The order of operation is PEMDAS. Please excuse my dear Aunt Sally. That's the typical mnemonic device that we use for that thing, if you recall from previous years of schooling. Now, what we don't necessarily cover is how, when they interact consecutively, how do we deal with those? Like, when we look at PEMDAS, it's more like this. Like, we certainly do parentheses first, then we do exponents. Now, multiplication and division essentially happen at the same time. So if we have both things happening, then we tend to go left to right. Okay? Same thing is true for addition and subtraction. If we have addition and subtraction happening at the same time, even if the subtraction comes before the addition, we'll do the subtraction first and then the addition. And that's where some people get into the trouble if they haven't looked at this in a long time. Let's see. I'm going to find an example for us. This is problem looking for a good one. So for example, if we just have 4 minus 2 times 3, we know that we do the multiplication first and then the subtraction. So 4 minus 6, which gives us a negative 2. we have 2 minus 7 plus 8. Whenever we have minus and plus together like this, my recommendation is to work from left to right. So do 2 minus 7 first, which is negative 5, and then add the 8 second, which gives us the 3. Okay. A lot of people want to add the 7 and the 8 first, and they make that like a 15, but then they do 2 minus 15. You get a completely different answer there. Okay. Now, if we remember that this is actually a negative 7, and then add the 8 to that, then there's no harm in doing that one first. As long as we attach the negative sign, the minus subtraction, as a negative sign to that number. So there's ways around that confusion that a lot of people have. Alright. This is page 9, number 22. I have no idea why they want us to do this section right now, although supposedly it's pertinent to what follows. That's the whole point of having it here. So I have no idea what you're doing next after matrices. I guess that's the issue. Okay. So we have 8. Now, we want to do our exponent first. That's negative 4 squared is 16. We handle the parentheses next, so minus of negative 12 will be plus. Yeah, this is like a vacation from the matrices. That doesn't mean it's time to drink yet, though. And again, working from left to right, 8 minus 16, negative 8, plus 12 gives us the 4. Okay. Again, it's just making sure we are very what's a good word? Specific is a good word. Precise. Making sure we're very precise in following the steps that we need to take to complete the calculation. Okay. 24. This is a little bit more involved. 2 parentheses 3 minus 7 plus 4 parentheses 8 divided by, and then 4 parentheses negative 3 plus negative 3 times negative 2. Now, in a problem such as this, when we see this fraction bar, we see this division sign right through the middle of everything, that is actually a natural separator of terms in an expression. And what we'll want to do is we'll simplify what's on the numerator by itself first. We'll simplify what's on the denominator by itself second. And then once those two numbers are taken care of, we'll just divide by whatever is left over. We work inside the parentheses. 3 minus 7 is negative 4. Nothing else in parentheses need to be simplified. Now we can do each of these multiplications, because we have 4 multiplications that have to take place next. 2 times negative 4 is negative 8. 4 times 8, 32. 4 times negative 3 is negative 12. And negative 3 times negative 2 is positive 6. We then do our additions, top and bottom. Negative 8 plus 32 is 24. Negative 12 plus 6 is negative 6. And then we divide. 24 divided by negative 6, negative 4. Okay. These problems really don't get much harder than this. Let's do 28. So 6 squared minus 3 times root 25 over square root of 6 squared plus 13. Okay. Now here we introduce the square root, but the square root is what works as a delineating term in the same way as a parenthesis. So basically the square root separates one piece of the problem from the rest of it. So just like we work inside parentheses first, we also work inside square roots first. So in this case, the first thing we want to do is simplify what's under the square root. Okay. So we have 6 squared, which is 36. Plus 13, and we'll go ahead and add the 36 and the 13. Which is 49. And then after this, we can go ahead and complete our square roots. Square root of 25 is 5. Square root of 49 is 7. Next we do our exponent, 6 squared. So that's 36. We do our multiplication, 15. Then subtract on top. So 21, and then divided by 7, we complete our last operation there, which is a 3. Alright, and that's really all there is to it. I just feel really odd teaching that in this class. I feel like we've done so many things that are harder than that. Why do we teach that now? But it's not for me to answer, that's true. That's what I've been given to do. Luckily, not that difficult. Okay. I think we can go ahead and stop there. That's really the only part I wanted to focus on in section 1 anyway. Everything else is even easier than that, which is not a bad thing, but I just don't think I need to actually cover the rest of that because I feel like everyone's going to be okay with it. And I think it's always nice to have a little reminder on the order of operations because that's one place where I do see students, even at the calculus level, they still make mistakes on that stuff. So it's worth going over a little bit more, I think. But the main thing is just being careful, really. That's really what it amounts to, and that's why they my calc students make mistakes sometimes is that they're not being careful. So, same thing of students of all levels. Just be careful. All right. So let's stop there, and on Wednesday we'll continue. If you have any more questions on matrices or similar, let me know. We can work on it. Otherwise, we'll continue from here. We'll eventually get to solving polynomial equations in Chapter 1. So it does get a little bit more difficult or more involved. So anyway, y'all take care. Have a good day, and we will do this again Wednesday. Bye. Yeah, hopefully that was helpful with that word problem, Geneva.